Hi, I am Jaiteja, PhD student at IISc, working with Professor Soma Biswas. We present our work going on data efficient class incremental learning in Doctoral Symposium track at AIML Systems 2022. Ability to learn from continuously evolving data is very important for real world applications. For example, in autonomous vehicle scenario, the model has learned to classify some set of categories, and tomorrow there is a chance to get some new set of categories from new classes. In real world, collecting data across all categories at the same time is difficult. So the model has to update its knowledge on these new categories without forgetting what it has learned. And at the same time, whenever this new classes arrives, the world class data can't be available due to security or privacy issues. The simple fine tuning of model on this new data leads to a problem called catastrophic forgetting, where it will forget all the classes seen earlier. Even if complete old data is available, it is computationally expensive to train a model from scratch at each task. So, class incremental learning addresses all these issues where model tries to update its knowledge continuously when the set of new classes are available. Here, once the model 0 learned on D0, also referred as a base task or task 0, at next incremental step, model has to learn new classes D1 with the help of model 0 knowledge without having access to data D0. So, at the end of each incremental step, the model 1 has to predict all the classes from D0 and D1. As we know, deep neural networks have shown impressive performance over various tasks, but requires large amount of annotated data for training. In real time, it's really hard to gather that much amount of annotated data. So the intersection of class incremental learning with less amount of annotated data leads to data efficient class incremental learning problems. So in traditional class incremental learning, at each task, model have access to large amount of labeled present task data with few examples from old task. But in future class incremental learning, at each task, model have access to very few labeled data with old task class prototypes. As we know, in real time data collecting unlabeled data is easy compared to labeled data. So in generalized semi-supervised CIL, at each task model have access to both these labeled and unlabeled data. To make the scenario more realistic, the labeled data can come from few data samples from new classes, but unlabeled data can come from present task, old task or outlier. So currently we are working on these FSCIL and GSSCIL problems. So coming to FSCIL, the major challenge here is the overfitting on new classes due to limited amount of labeled data and catastrophic forgetting on old classes. So before going to proposed approach for FSCIL, first we will see what exactly stochastic classifiers are. Let us consider a standard classifier phi for a given input image x from class I. Let us denote its feature vector is f of x. The classifier weight corresponding to ith class is phi I and jth class is phi j. The green shaded area shows the region where f of x is correctly classified to ith class, and MIC is the classification boundary between these two classes. Now, instead of single classifier, let us learn two different classifiers for each class, which leads to a more margin between these two classes and make them very well clustered. Now, using this stochastic classifier at classification head resembles the use of these multiple classifiers, where each classifier here is sampled from a distribution. Empirically, we shown that using this sample classifier for learning new classes in FSCIL mitigates the overfitting problem. And this is our final S3C framework. So due to presence of few labeled samples from new classes, it's very important to learn well generalized base task model. For this purpose, we have used a rotation based self-supervised technique in our algorithm. Here, each image is rotated into 4 rotations and treated as a separate class. And each class is a stochastic classifier and trained with our LS3C objective. In common practice, prototypes will be stored at each incremental step to mitigate catastrophic forgetting. So at each incremental task, the model stochastic classifiers are tuned with these both prototypes and LS3 loss on this new class data. At test time, we know the image rotation, so we used aggregate score from individual classifiers for final prediction. Slide shows the experiment results on CFAR and mini ImageNet datasets. Both have 100 classes, the number of base classes are 60 and 555 classes are added continuously. And each class have 5 samples. We observed that 4.8 and 4.5 improvement over state of art technique CEC on both datasets. And figure shows the TSNE plot between CEC and our proposed approach S3C. We have observed well clusters when we trained with S3C. Now coming to generalized semi-supervised class incremental learning, here utilizing the unlabeled data to learn new tasks is a major challenge. And we have proposed a simple and effective pseudo-labeling approach to address this GSS-CAL problem. And coming to conclusion, we proposed a novel framework S3C to address FSCAL task, and we proposed a data efficient CAL protocol named GSS-CAL, and we addressed with simple and effective pseudo-labeling approach ESPN, and extensive experiments shown the effectiveness of our proposed approaches. Currently, we are working on re-ranking approaches for S3C at test time and try to incorporate semantic information in FSCL. And another problem, we are working on continual test time domain adaptation, where different domains are adapted continuously. Future, we are planning to work on unsupervised class incremental learning and how vision transformers are working in these incremental learning settings. And these are the publications from our work, and thank you.